Okay, so let's actually impose an initial condition on a complex case problem. Just to make it clear, because I don't want you to work twice as much as necessary, right? I mean, you have a solution in two versions, right? I mean, you don't do it twice. When you choose your eigenvector, you make your choice, be done with it, and finish the problem. Here, I provided a solution in two ways because I obtained the eigenvector in two ways, one equation or the other. So that results in different components for the complex eigenvector, so therefore the solution can be written in a different way. But in practice, you do it only once. I just want to do this initial value problem using both versions to convince yourselves that although these looks quite different, I mean 2, 1 compared to 1, 1 doesn't seem to be in the same ballpark, or 0, 1 versus -1, 0, right, for the eigenvector. Although it looks quite different, you'll see that it represents essentially the same solution. And one nice check to see that is when I impose an initial condition, I should get a unique solution. That's the general, one of the most important theorems in differential equations, that systems like this should have a unique solution for a given initial condition. Furthermore, when you impose the initial condition in the complex case, it's actually easier than it may look, because the presence of sine and cosine will create lots of zeros. Remember, when you plug in 0 for t, sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1. So keep that in mind, and notice that when you impose this initial condition, so let's use the first version here, x of 0 equals e to the 0 is 1, so you're left with c1. And be careful here on the first parenthesis, what survives is just 1, 1. Because cosine of 0 is 1, sine of 0 is 0, so this part goes away, okay? So you're left with c1 times 1, 1, and then plus, let's see what survives in the second component. Well, e to the 0 again is 1, so that's c2. Sine of 0 is 0, that goes away, you're left with -1, 0, because cosine of 0 is 1. And then you set that equal to the initial conditions, which is 1, 1 in my case. So you form a system in C1 and C2 just like before. Let's solve it via matrix computation. Remember, if you look at the first component, that's C1 times 1 plus C2 times -1 equals 1. C1 times 1 plus 0 equals 1. So it's quite easy. And C1 becomes 1 from the second equation, and if I plug it in into the first, I get C2 equals 0. Okay, so then what's my unique solution corresponding to this initial condition? Well, if C1 equals 1 and C2 is 0, this part goes away completely. So my solution then is going to be e to the -2t. And by the way, at this point, it's customary, once you find C1 and C2, it's customary to combine everything into a single vector. Just to write your solution in a nicer form, this part here is 1 times cosine minus -1 sine. So that becomes cosine of t plus sine of t. And the second component is 1 times cosine minus 0 times sine. So that's scalar multiplication and addition of matrices. So the second component is cosine of t. And you can leave the exponent outside as a scalar, but realize that if someone asks you in the original component of the system, like, you know, it's a system of 3 equations and 2 unknowns, okay? What is the first unknown? That's e to the -2t times the whole cosine plus sine. The second unknown is e to the -2t times cosine of t. But you can leave it in the matrix form without any problems. So if I use now the second version of the solution to find C1 and C2, now the C1 and C2 will be different, but when I simplify everything, I better get the same answer. If I don't, that means I made a mistake somewhere. So let's just do that. Again, in practice, you do it only once, but I want to do it with the other version as well. So we're looking at the second version of the solution, plug in 0 for t. And by the way, at all points, it's worthwhile to pause me and try to do the steps ahead of time to see if you got the whole idea. So C1 e to the 0, which is C1. Here again, sign of 0 goes away, and only 2 1 survives. C2 e to the 0. Sign of 0 is 0, and this is just 0. Oops. I just noticed a typo here. So this is cosine of t. Just notice that, otherwise nothing would have survived here, right? So cosine of t minus sine, sine plus cosine. Okay, so sine of 0 is 0, and you're left with 0, 1 times cosine of 0, which is 1. Okay, so once again, this is cosine of t. So please change it from sine of t to cosine of t. And this is equal to 1, 1. All right, what is the system that comes from here? That's 2c1 equals 1. 2c1 plus 0 equals 1. c1 plus c2 equals 1. So I get c1 equals 1/2. And it's easy to see from the second equation that c2 is also 1/2. We have to do more simplification here to actually get this form. So let's just do that. X bar equals what? C1 is 1/2 e to the minus 2t. Let's bring this into a single vector, this parenthesis here. So that's going to be 2 cosine of t, 1 cosine minus sine. That becomes cosine of t minus sine of t. So obviously, see, this choice was easier because I was lucky with c2 to be 0. Now the simplification, if I have to perform it, takes more time. Plus 1/2 e to the minus 2t. Let's combine this into a single vector as well. 2 sine plus 0 cosine, that's 2 sine of t. And then sine plus cosine is the second component. Moving on with some algebra, we can pull out 1/2 e to the minus 2t between the two matrices, right? I mean, we can pull out as a common factor and add the two matrices. When I add 2 cosine plus 2 sine, I can pull out 2. Cosine of t minus sine of t, and then plus sine of t plus cosine of t. Sine cancels, and I hope you get the idea how it goes from here. 1/2 e to the minus 2t. On the top is 2 cosine plus sine. Oops, out of range a little bit. So 2 quantity cosine of t plus sine of t. There you go. Here is 2 cosine of t if I combine them. Okay, so I can bring now 1/2 inside. Scalar multiplication, 1/2 times 2 cosine plus sine. And 1/2 times 2 cosine of t. Anyway, so 1/2 cancels with 2. And I hope everybody agrees that we get the same solution as expected. No surprise, right? I mean, that's what should happen if we write the general solution in the correct way. So at this point, remember, general solutions can be written in a different way, especially since eigenvectors are not unique. Again, it's very repeating. Eigenvectors are not unique. You have different ways to write a general solution. Still correct. Choose the easiest one, computationally speaking. Especially in the complex case, avoid fractions, especially avoid fractions with I at the bottom. And then if you're correct, of course, any initial condition should provide the same solution. Before we call it a day, because it's such a nice area left here that I don't want to waste, let's actually do one more complex case quickly. Not the full problem. Just a matrix and extracting the eigenvector. And then just one last remark on how to avoid fractions in some cases that may appear. So So let's say another matrix is -4, -2, and 1, -2. Once again, get used to that shortcut because I'm using it in my teaching and it's useful to you as well. So that shortcut comes from setting up the characteristic equation, right? Go directly with lambda squared minus the trace. Trace is -6. -4, -2. Just don't forget the extra negative here. Determinant -4 times -2 is 8. Minus -2 becomes +2. Right? So the characteristic equation would be lambda squared plus 6 lambda plus 10 equals 0. With the quadratic formula, lambda is -6 plus -36 -40 over 2. By the way, again, just pause and do the work yourself and then check when you're done. It's a good thing to do at this point, to actually compute the eigenvalues and vectors yourself for this example. The quicker you do it, the better, so that it's fresh in your memory. So this is -6 plus root -4, 30 -40. So lambda would be -3 plus minus, this is 2i, so divided by 2, that's plus minus I. So alpha is equal to -3, beta is equal to 1. And now you're setting the system to find the complex eigenvector. Okay, choose the one with plus. Remember, it doesn't matter which, just make a choice and stick to it. Subtract -3 plus I from the main diagonal. And set up the system for the eigenvector. Now let's go out of range here. So v1, v2, 0, 0. There we go. Let's see. -4 plus 3, that's -1 minus I. -2, 1, -2 plus 3, that's 1 minus I. You're going to do it only once, right? You're not going to choose both equations. Just choose the one that you like. I'm going to choose the second one. Feels easier. But you can choose any equation you want, right? So v1, 1 times v1 plus 1 minus I v2 equals 0. And let's actually do it in one step here. What's the best substitution here for v1 and v2? The easiest thing is to plug in 1 for v2. Notice here, because that avoids fraction. 1 for v2. v1, move that over, becomes -1 plus I. So that's the eigenvector, -1 plus I and 1. Let me write it here again. -1 plus I and 1. And of course, write 1 as combination real part, imaginary part. 1 plus 0i. So then you could quickly see the split into real part -1, 1 plus, I'm not going to have room here, plus I times 1, 0. Almost out of range. I thought I have more space than I had. So 1 minus 1, 1, 1, 0. And this will be P. And of course, 1, 0 will be Q bar. Yeah. I'm going to just write it here. So you end up with -1 plus I, 1 plus 0i, and that splits into -1, 1 plus 1, 0i. Okay, so this is P and this is Q bar. And if that's part of the differential system, that's how you go and proceed with it. I'm not going to make another part. One thing I wanted to mention, and I'm going to just erase a couple of things here to mention now. when you try to avoid fraction, it's not always, and I already showed you an example in the complex case, it's not always the case that you need, you actually write the, so let me actually raise this last example. So it's not the case that you always plug in 1 to avoid fractions. I mean, in most of the examples, you'll see 1 is, or -1 is the best choice, right, to avoid fractions when you extract the eigenvector. But there are many situations in which the best choice is another number, right? So for example, let's say in the process of finding the eigenvector, you end up with this equation, 2v1 minus 5v2 equals 0. If you want to avoid fractions, 1 is not a good choice, right? I mean, if you choose v1 to be 1, obviously v2 will be 2 over 5. If you choose v2 to be 1, then v1 is 5 over 2. So neither of them will give you no fractions. Fractions are fine, but if you want to avoid fractions for a nice computation, you have to choose a different coefficient. So anyway, the magic coefficient to choose, or the magic value to choose, is the one that allows you to make some simplification with the other coefficient. So for example, one choice is to give 5 to v1, and that becomes 2 times 5 minus 5 times v2, cancel 5, v2 would be 2, and then a version of the eigenvector therefore is 5, 2. Or you could choose to let v2 to be 2, which will cancel with this 2. So you can let v2 to be 2, and then we have 2v1 minus 5 times 2 equals 0, cancel the 2, and then v1 will be 5. Did I do that the wrong way? So v1 equals 5. No, I mean that's, yeah, I mean obviously it's the same thing, yeah. So I mean either you start with v1 equals 5, same thing obviously, because it's the same combination. So obviously you start with this one to be 5 or this one to be 2, it's the same thing. I mean you get the cancellation that you need to avoid fractions. So anyway, that concludes the chapter on, I mean the subject on solving the homogeneous system of linear equations. The next part will be mostly on Camtasia on the computer screen, because I want to show you the geometric properties of solutions around the origin, around the equilibrium point for a linear system. And after that, we're going to finish the chapter with the non-homogeneous part, which will actually be easier because it will basically be the same method you use for single ODEs. So with that being in mind, let's finish for today, and I'll see you next time.